where we talk about one which is also known as holy fibers, correct? Holy fibers based on basically they are also nothing but photonic crystal fiber, okay, fibers. And the technique used is basically functionally graded materials, okay. They are functionally graded materials, and that means the refractive index, right, is spatially, right, controlled such a way that we end up with the fiber within light can be trapped either in the core, or it can also transmit through the cladding region, right, etc. What it the advantages with such hollow fibers is, if we would like to analyze, let us say as some, so one advantage is in terms of pumping and right, let us say amplification of light, amplification of light is possible, okay. We will talk about these aspects, what is pumping, what is amplification of light, etc., at a later stage when we talk about light sources. So, optical fibers can act as an amplifying material, and we can use a pumping light to excite that, right, amplifying material excitation. For that purpose, we can make use of such fibers to allow pump light to pass through the cladding region and right, allow amplification of light in the core region, okay. That is possible. Second point is the hollow cores, okay, can also be used in order to like say analyte can be inside and we can analyze the sample, right. So, the analyte or the right or substance, right, maybe liquid, maybe gaseous, right, material can be, it can pass through the fiber, it can pass through the hollow core fiber, right. So, and we can study the transmission or some other optical characteristics concerning this liquid or gas medium with a very small volume, right. It can trap a very small volume and still it can help us to characterize basically spectral characteristics can be captured. The in this one is holy fiber, the other one are hollow core fibers, okay. So, in this hollow core fibers the it has a glass or a plastic tube, okay. It's a fiber size maybe of the order of right few hundred, maybe let us say 500 micrometer to 1500 micrometer, okay. So, basically right a few hundred micrometer to 1500 micrometer is the core size, okay. And this core size, and inside of this of course this material is right coated with, let us say metallic coating, okay, aluminum or metallic coating, okay, for a visible light to get transmitted through, okay, for visible light, okay, visible light can easily transmit through such fiber. The outer right part may be a protecting layer as well, there may be a protecting layer, right, a protecting layer. here right, we use reflection as the right way that the light get transmitted through. There is another way, instead of it is similar hollow core fiber, and instead of metallic coating, it will have something like a clad region, then dielectric coating. Okay, right. So, this is right outer, let us say, jacket. So, outer layer, the glass layer, okay, outer layer here. So, it may be made up of glass or plastic, and inside it will have right, say, clad layer, or right basically a clad layer with a slightly less refractive index, okay, a clad layer, and inner one is dielectric coating, okay, to allow infrared light, okay, near infrared or infrared, right. So, infrared, right, okay, right, depending upon the type of dielectric coating, it can allow 2 micrometer to 10-12 micrometer light to transmit through this hollow core, and internal diameter may be of the order of 500 to 1500 micrometer. Okay. So, it allows some medium which we want to characterize can be stored right in this. So, very less volume, because the diameter is small, very less volume, light, optical light can propagate through this. So, very good coupling, right, with the light with this medium to be characterized, and we can easily capture the information. So, they have some specific applications, this hollow core fibers, but it can be used. Of course, in lasers it is also possible to certain extent. Of course, damage threshold is quite low, but it is possible to transmit even the pulsed laser beam through this, alright. However, damage threshold is very low. So, it is right, if the intensity of the laser is large, it will damage this type of fibers easily, but it is possible. So, right now we are going towards the next topic concerning different types of optical sources. Okay. Now, when we talk about optical sources, let us say the optical sources as such can be based on, of course, we know sunlight is one very good, right, important optical source, but for our applications, right, biophotonics related applications, we need a source, right, which can be which whose light can be used for a particular wavelength, or which can be controlled in terms of its right coupling efficiency, means coupling of that light source with the measurement system, etc. So, one what we know about is right incandescent lamps, correct. Okay, incandescent lamp. So, in case of so this is one incandescent lamp, the other one is fluorescence or fluorescent lamp. Okay. Then light emitting diodes, and lasers. Okay. The lasers again have different this thing, it can be solid state or gaseous or liquid or semiconductor based, right. So, okay, when I say solid state means, of course, semiconductor also comes, right, as a, it is a solid state material. However, here we talk about optical crystal base, okay, crystal base solid state lasers. Okay. So, now when we talk about incandescent lamp, it is basically the energy conversion is through electrical, right, electrical to heat. So, basically light, right. So, we may be using a filament and then electrical current passes through this filament, I square R effect will generate heat, and in turn we will see the output in terms of optical, right, output. It may have, depending upon the type of filament what we use and the heat what is generated, we will be able to get wavelengths ranging from let us say some visible range to near infrared range. Okay. So, one example of incandescent lamp we know, right, the conventional bulbs are also one type of incandescent lamp, and but there the efficiency is quite low, right. The efficiency of incandescent lamp is quite low in terms of electrical to output optical efficiency. Over and above, the heat generated is also, because efficiency is low, connected with even heat generation is large. So, handling such incandescent lamp with high power is one right issue. Second point is how to couple the, it is not coherent, right, it is incoherent light source, and how to couple that light source to certain, right, measuring systems, maybe optical fibers, etcetera, it is not very easy. So, it provides incoherent, right, incoherent light source, right, and efficiency is low and heat generation is quite large, okay, with respect to the output. Okay. Still it can be used, we will see some applications where we can still make use of this filaments, tungsten wire filaments, or right, other materials which can be used as a filament to generate certain amount of such optical, right, light. So, this is about incandescent lamp. Now, fluorescent lamps, or maybe first I will give you example of this incandescent lamp itself before we go, so that it will be, we need not come back. So, of course, as I told you, arc lamp, tungsten filament lamp. So, okay, maybe okay. So, it is, one is, okay, tungsten filament lamp. Okay. And maybe after some time I will show you the spectra what is being emitted in terms of optical, right, wavelengths, etcetera. This is, right, one very potent source, the fluorescent lamp and arc lamps, fluorescent and arc lamps are basically electrical input gets converted into an arc, right, and which generates. So, basic plasma formation, plasma is formed and optical light is observed. okay, arc lengths. So, there are different types of arc lengths, xenon, right, krypton, right, deuterium D2 type arc lengths, etc. They have mercury, of course, mercury is also there. We know one of the fluorescent tube, what we see fluorescent tube is also having, right, mercury. I will show you what is the spectrum for that also. Just mercury, xenon, krypton, deuterium are the different types of such arc lengths. They are also very useful in order to right, use, means they are useful for spectroscopy applications, etc. And they are also being used in, right, biophotonics devices. So, these are the arc lengths. Maybe I will show you some examples. See this visible spectrum, what is shown over here. If you would like to see it of your own, right, you can see it easily. How do you know about it? You can use a CD, compact disc. Okay, just see the surface of the compact disc. It is acting as a grating structure because it has micro such, right, durations, and it acts as a grating structure. So, when you see the tube light and see this, you will be able to see the spectra, and it will really, it will show the similar such spectrum. There will be some within the spectra, there will be some region which will have little more intensity in terms of. So, these are the wavelengths which will have, right. So, 546 is around green region. So, you will see in the CD a green region which is slightly more bright spot within the green region, because green region may have a wavelength range, but the mercury light, so, which is emitted from this mercury arc length, which will have 546 nanometer in certain region. So, you will see some bright region, you will see some such lines, layers, okay, which is indirectly representing some of those mercury arc emissions. 436 nanometer which is near blue, then 365 which is near UV range, maybe we may not be able to see it clearly, okay, with our naked eye, but that is very useful for certain other applications. But these lines are useful for certain applications, okay, for it is basically for measurement applications. This I have taken from Newport, right, database for mercury lamp. What is the spectrum? So, you can see as it is shown in the previous slide, up to UV, see, we know of up to 380 nanometer, so it is a UV. Beyond 380 nanometer, or it is written here also, of course ranges may little bit vary. So, there is UV spectrum, right, in this region. So, up to 350 to 400 or 320 to 400 nanometer is treated as UVA. Then UVB 280 to 320 nanometer, and UVC 250 to 280 nanometer, okay. And below this comes vacuum ultraviolet. Below 200 nanometer is vacuum ultraviolet region, okay. Below few tens of nanometer, it is extreme ultraviolet, EUV, okay. So, these are the range. So, here below 200 nanometer approximately, and here below maybe 15 nanometer or so. So, there are some light sources which can allow, right, extreme UV light sources for other applications, okay. We will not talk about this. Now, visible range is between 400 and 700 nanometer. So, this is visible range. So, blue, right, green, yellow, orange, this part, and then red 600 nanometer region, etc. So, 400 to 700 nanometer, and infrared, as I told you, near infrared is up to, it depends upon textbooks and various other convention, around 2 micrometer we can say, right, near infrared, near IR 700 800 nanometer onwards, okay, and then it goes mid IR range 2 to 5 micrometer and or 2 to 8 micrometer, and then beyond that is far infrared. Now, you can see that mercury has a broad output spectrum, somewhat flat in this region, somewhat flat, okay, while here you have various mercury emission lines, as we had seen in the previous plot, right. All these emission lines which are seen here, okay, they are nothing but they are here, all these lines, correct. We can make use of some of those emission lines for measurements or a flat region, but if you compare it with xenon lamp has somewhat flat region, but you can see that around 800 around 800 to 1000 nanometer, they have various such emission lines, okay, emission lines 800, 895, 900, 980 nanometer, etc. Some emission lines are there, or more or less in up to 2.4, 2.5 micrometer, it has a right a flat region. Okay. So, xenon lamps are also very useful for certain applications, for calibration applications, as well as measurements also applications, and it has a broadband spectrum from 160 nanometer to 2000 nanometer, etc. So, this is again xenon lamp with, right, you can see around 800 to 1000 nanometer. There are some clear right emission lines, but otherwise it is a flat spectrum. Now, deuterium lamp is based on D2 light source, and tungsten halogen lamp means tungsten mixed with some halogen gas allows tungsten filament to is used, and then that energy means at high temperature the arc tungsten halogen lamp will produce an arc, and that arc is also having a flat spectrum up to 2.5 micrometer. Okay. So, depending upon our applications, etc., it can be used. And deuterium lamp, this is quartz tungsten halogen lamp, you can see it is a flat beam. So, this type of sources are useful for calibration purpose, because their spectrum is very well defined, you can calibrate spectrometers, etc. Why, whatever just now I am talking is very useful when we use it for measurement system, no, biophotonics, we should know what is the source, right, and what is its characteristics. That helps us when we interact, when it interacts with biophotonics, right, for sensing, etc., it is useful. Now, deuterium lamp, they have some specific lines in UV region, it has some optical emission 200 to 300 nanometer, and some specific lines around 600 nanometer or around 450 or 480 nanometer or so. Okay. So, they have some specific lines, they are useful, particularly deuterium lamp is useful for UV as a UV light source. Okay. It is useful for biophotonics devices. Okay. So, these are some of the light sources which are based on conversion of conversion from electrical input to either arc formation or heat generation, and then providing the light output. And this light whatever is emitted from this type of devices, maybe are there any 1 minute, I will show you how the device is also, how they look like, sorry, how they look like is there. Okay, they see the some of the arc lamps, no, they something look like a tube, or it can be a small device. So, the optical light which is emitted will be coming out from this output and or mercury. So, it will look like, it will have anode, a positive terminal, cathode which is negative terminal, and then arc is generated by applying a very high voltage to this arc lamp, and the let us say mercury or xenon gas etc., which is filled, or krypton at a high pressure will glow, right, with as the arc is formed, and that glow is basically nothing but a light with a spectrum ranging from, right, UV range to near infrared range etc. Okay. So, this type of light sources are used. Now, you can easily understand that it is coupling in terms of for coupling we need some type of optical other components to couple the light for our measurements etc. Over and above, as I told you, they have very means the efficiency is also a question, heat generation, right, dissipation of heat, and then cooling etc., all such aspects are becomes very important. So, the others way is we can use of light emitting diodes, okay, which are semiconductor based devices for generating the optical, right, light of different wavelengths. And in case of light emitting diode, basically as we know, a semiconductor device will have right, a valence band, right, and a conduction band, right, and this is right, approximately, let us say there is it has a band gap. Okay. So, and basic electron when we excite this material by applying an external electrical, right, input, then the from the valence band, right, depending upon the doping characteristics, okay, the electrons can jump to the conduction band or get transferred to the conduction band, and then when this electron combines with the hole over here. So, this combining, right. So, electron combining with hole will emit optical, right, or basically right, optical out will result in an optical output. So, this is because of the electron hole, right, combination. So, it is basically recombining the electron with the hole will emit, right, will emit optical light, and this optical output corresponds to the band gap energy. Okay. So, that means the photon frequency is nothing but it corresponds to the band gap of this, right, light emitting diode material. Okay. So, now basically in case of light emitting diode, semiconductor material is to be doped with certain right, either p type or n type right, materials with the doping concentration should be very large. Okay. So, basically how it will look like, we will see. Oh, sorry. Okay. So, maybe in a very simple way. So, when we consider let us say NP junction of a semiconductor material, and when we go with a positive bias. Okay. So, what is expected? Current flow will be in this direction, and the correspondingly the electron, right, will be traveling in this direction. So, basically from n type the electron will travel to the p type, okay, then but at the junction they will get concentrated. Okay. So, when we apply a positive bias, the electrons which are travelling from n type to p type at the in the junction region, they will have much more high density. The electrical field concentrated over here will be very large in this junction region. Okay. And this electrons will be means the numbers will be large, and there is a good chance that they combine with the holes over here. Okay. Now, see in terms of Fermi level, what it means, Fermi level represents the probability of basically electron to be there as a, let us say Fermi level represents around 50% or more electrons, presence of that level. So, here you can see n type near the conduction band the Fermi level would be located, because the probability of electrons will be large, indirectly it represents that indirectly, and p type it will be near this valence band. Okay. Because the number of electrons presence of up to means you can say that the large number of electrons presence will be near valence band in p type, and at the junction region the distribution will look like this, the Fermi level will look like this. So, this because of this the combination, the recombination comes into picture with the electrons, probability of recombining with the hole increases in this region. So, when they combine with the hole, they will emit the energy optical light with the frequency matching with the band gap, and this band gaps are in terms of momentum, mismatch, etc. That there are certain requirements from the quantum physics point of view. The semiconductor material conduction band has this type of energy electrical energy distribution, and valence band will have this type of energy distribution. And if it is a direct band gap material semiconductor, in that case when electron combines with the hole, both this valence band and conduction band, this one will have this means the basically the momentum of this electron as well as hole will be such that it is matching with each other. So, the photon is emitted by conserving the energy as well as momentum. Energy conservation corresponds to the photon emission corresponding to the band gap, and momentum conservation allows efficient generation of this photon. But in case of an indirect semiconductor material, band gap material, what happens, this momentum mismatch is observed between the electron and the hole, okay, and this momentum mismatch results in a photon generation along with some phononic some losses, okay, which because so as to conserve the momentum there has to be some other particle basically which should take care of this momentum mismatch through this phononic emission, and this results in inefficient emission of photon. So, basically the inefficiency in the indirect band gap material is very large, and hence generally in case of laser optical diodes etc., we prefer direct band gap materials. Silicon and germanium are not direct band gap, they are indirect band gap materials. Although they are very good semiconductor, right, from the electronics point of view materials, however, they are indirect band gap materials, and that is why from the optoelectronics point of view they are not very efficient, right, material in terms of optical this, right, photo generation. So, we are not using such material, but we use different other some different materials which can allow right light. Maybe I will show you the list, then we will come back to this. So, there are various such right 3, 5 group and 2, 6 group semiconductor materials in the periodic tables. Okay. Other than the silicon and germanium, so 3, 5 group materials when we combine, or 2, 6 group materials when we combine, it results in an right energy gap, semiconductor material with a certain energy gap, and corresponding to the band gap of this semiconducting material, we get the output right emissions at different wavelengths. Okay. So, this gallium arsenide is a very well known gallium arsenide, or aluminum gallium arsenide. Basically they will also have wavelengths in 1.5 wavelength. Maybe we will see right here it is not included, but aluminum gallium arsenide is also available at around 1.5 micrometer or so, we will get the light. So, this materials, their energy band gap allows output wavelength around 800 nanometer, 1.5 micrometer, around that, etc. Now, 800 nanometer, you know, it was useful for compact disc. So, this was the source which was used as an optical diode. Of course, there was some slight difference. It was not used as a light emitting diode, what I described just now, it was used as a laser. So, what is the difference between light emitting diode semiconductor and a similar material, but as a laser? We will see it in the next few slides, but you can see that depending upon the band gap, different wavelengths, and relationship is right very simple. This is nothing but the band gap, right, and nu is nothing but c by lambda. C is the right speed of light, lambda is the wavelength. So, correspondingly we can derive the optical right wavelength which are described over here. You can see that if we use large band gap material such as gallium nitride or aluminum nitride, we will end up with a UV range output. Okay. While if we use smaller band gap materials, we end up with a near infrared or little right mid infrared range output wavelength. The smaller the band gap, so right, the it's this type of material has to be cooled, otherwise at room temperature itself, right, there will be electron transitions, etc., they will disturb the output, right, very much. Okay, we will stop here, 9:52. So, we will continue. Now, we will try to see in the next class how LEDs, right, are different from the laser, and we should also learn, then we will learn about what it means by laser, right, and what are the different wavelengths, laser wavelengths which are available in terms of based on the material what we use. Okay. So, we will stop here.